Well, good afternoon, folks. I am here to talk to you today about the volcano Hekla. It's also known as the Icelandic Gateway to Hell. We are located at 63.9923 degrees to the north and 19.6658 degrees to the west. We are approximately 160 kilometers from the Icelandic capital of Reykjavik. And in terms of size, our height is almost 1,500 meters high, or coming in at 1,491. We have a ridge length of 40 kilometers, and we are part of the East Volcanic Zone. This zone contains the most active volcanoes that are in this region. And what's important to us about all of this is that this is actually on one of our major airline routes for a global scale. Everybody travels this if we're anywhere near the Iceland area. So, to begin talking about this volcano, okay, the history of it, the eruptions we have recorded since all the way back to the Holocene period, which is roughly 1,000 years before Common Era. We have found evidence of this in the Scottish peat bogs that are in the northern British Isles. Our first recorded eruption was during 1104, which was in the Middle Ages, and it was recorded by monks and other Christians that were out exploring at the time. That explosion covered most of Iceland and Tefra. Largely a rhyodacite tephra composed of dacite and rhyolite with a largely high silica content and low alkali content. The volcanic explosivity index was 5 for this, which would have been terrifying at the time, given the cataclysmic nature of the explosion and the tall injection cloud through the troposphere and into the stratosphere. It was categorized as a Pelian or a Plinian eruption, which would have closely resembled the explosiveness that people experienced when Mount Vesuvius went off. This is part of where the gate to hell reference comes from, was just the overall appearance of this must have just been enormous in size and enormous and scary, I guess, as you would want to look at it from even afar. From this initial documentation, we've determined that it basically erupts every 20 to 30 years. And they range anywhere for a VEI of 1 to a VEI of 4. Most of these are volcanic explosivity indexes of a 3, which falls in the Strombolian classification. And while it's dramatic in display, it's not as destructive as what the 1104 eruption was for us. Now, more recently, come on. There we go. My board doesn't like me some days. More recently, we had an eruption back in 2000. It started on the 26th of February of 2000, and it lasted for a total of 12 days. Now, what's odd about that one is it only had a 9-year dormancy period prior to the eruption before it, which was in 1991, and then approximately only a decade apart for the 1980 eruption and the 1970 eruption as well. So it's averaging once every 10 years in the last part of the 20th century that we had. Now, during this 12 days, this was a really, really short duration for Hekla, which was normal to be going on for months at a time. In this sense, the Hekla volcano is going to resemble the lava that was generously released that we see in Hawaii. But Hekla starts with something far more explosive than Hawaii, because Hawaii just kind of burbles and gurgles it out, whereas Hekla really does do something magnificent to see. Really large explosions and a great release all at once. Now, something that's been kind of new with this is that we found pyroclastic flows recently in the 2000 eruption, and since then we've been finding them as well. It progressed and fissures collapsed in Hekla, releasing several pyroclastic flows with varying compositions based on the fissure collapse location. So depending along this fissure where you were, we had different compositions of what actually came out of it, which that was a little bit of a rarity event as well, because we've been pretty accustomed to knowing what comes out of Hekla. Now, the multiple fissures and fissure collapses, the collapses not only fueled the lava and the pyroclastic composition, but it made a significant change in the crater topography too, due to the collapse not rebounding from lava flow. So basically we had this great big collapse, a great big hole, and the lava didn't fill it back in. That was something that was a little out of the ordinary with this eruption in 2000 as well. Now, the eruption products, of course, varied by area of the crater. Like I was saying, along the fissure and the crater itself, it was different depending on where you were. The next slide is the tephra that came out. Now, this was ejected during the initial moments of the eruption, and the largest amounts were part of the initial eruption. And while the pyroclastic flows continued as areas of fissure collapse occurred, the tephra was limited to the very beginning of this eruption. It didn't continue all the way through the eruption time frame. It was just initially, and then stopped. That was also another rarity or an oddity for us. Now, we only accumulated 1/1000th of a kilometer, which is a very, very thin layer of tephra. It spread north mostly into the uninhabited regions of Iceland, and it fell in some adjacent communities, but still, as I say, this was a very, very thin layer. This wasn't the normal kilometers thick. This was less than a meter, actually. If it was only 0.001 kilometers, this is just about a meter of deposit. Now, the total time of that eruption was 2 days, but over the 12-day period, it continued to act up. Now, it had a low silica composition, which is odd, and they tend to reflect large percentages of silica, but in 2000, it was some of the lowest that we had ever measured in any of those eruptions that we had found since 1104. So, let's get talking about the thing that was really different in comparison to everything that we've seen over the last 1,000 years for this volcano. This is the first time Hekla ever exhibited signs of a pyroclastic flow. That hasn't really happened before. Up until this point, it was only tephra and lava, which made it look like Hawaii, or seemed like the same type of volcanism that we see in Hawaii. Slow, well, high in magnitude, but not really pyroclastic style. This was really new, so we made sure we made note of that one. Most notable at the southern end of the fissure, the pyroclastic flows were found along the southern end of the fissure. It was also noted to have extended almost 2 kilometers past the lava deposits that came out of the volcano. So these flows went quite a distance past what normal lava did flow. On multiple fissures, the analysis has shown that the flows along the fissures began to collapse and fracture open again. That was also a little bit odd. Now, fine ash and 10 to 30 centimeter bombs, also known as cauliflower bombs, have been found here as well, and lithic fragments that are 5 to 10 centimeters in size, too. These are things that were new in comparison to the deposits that we've been finding since 1100 BCE. It extends past the lava flows themselves, which that was really weird, too, because now it's going out further than it ever has before. It forced a re-examination of what we know about Hekla, and it's going to take a little bit of re-examination and some more study to determine whether or not this is going to be a new feature for this volcano. Moving along, as for tectonic activity, as you can imagine, with an awful lot of volcanoes in an area, there's going to be a lot of tectonic activity as well. And this area has many structures, magma chambers, and earthquakes to go along with it. Now, along the northern part of the Atlantic Ridge, this seismic zone exists and is the northern point of the Atlantic crater. Not much earthquake activity usually comes before a Hekla eruption. So just because seismic activity increases, that's not really going to say, oh no, Hekla's going to go and blow, because that's not really the case. The earthquakes are not going to tell us that Hekla's going to blow. Historically, Hekla just blows, no warning. So, we did notice in the 2000 eruption, however, and unsure about prior eruptions because we weren't really present there to check the water table, but during the 2000 eruption, the water table dropped prior to the eruption. So there could be a correlation between the water table dropping and an imminent explosion of the volcano. More study needs to be done to follow that, too. We can't just go on one time. There we go. Sorry about that, folks. I didn't mean to delay that. Now, where are we? Oh, the lava. Okay. Yes, now, this here, the lava, it has a basaltic andesite composition to it, which is a silicon oxide or SiO2, and it comes in at roughly 55 to almost 60% weight percentages. The temperature here we found to be somewhere between 1,062 to 1,136 degrees Celsius, and the viscosity ranged anywhere between 103 and 108 pascals a second, which that's actually pretty fast. That's a pretty fast rate to run at. It had a rugged and a spiny surface. This texture developed because of the striking air temperature differences. We are talking Iceland. This isn't like Hawaii where it's 90-degree air temperature. Iceland, we were probably looking at like a 0-degree air temperature. So lava comes out, cools really fast, and creates a different type of feel, a different type of appearance, and that ended up being rugged and spiny. Usually, like Hawaii, for example, we would find like a more glassy texture to it, but that just isn't the case when we're in a frozen zone like Iceland. Discharge of the lava has always been highest in the initial hours. The lava flows were the most active during the first hours, and while they continued through the remainder of the eruption, the production was not as substantial as what the earlier eruptions starting that we know of back in 1104 did. We tended to get a lot more lava out of it early on, and over the years, over the centuries, less and less and less has been coming out of it. Does that mean that it might be slowing down, coming to a stop? No, it doesn't actually imply anything. It just means that it's been getting less and less over time. Maybe it's building up to something. We don't know. But nonetheless, it has been getting less, and it does look different because of the atmospheric conditions that are surrounding the volcano and the area in which it is found. Looking at the eruption of 2000, the petrology for it, okay, we found largely basaltic, andesite, and rhyolite. There were variations in MgO, TiO2, FeO, CaO, and P2O5. To help you out with that, it's magnesium oxide, titanium oxide, iron oxide, calcium oxide, and potassium oxide. There was a strong inflection in the aluminum oxide, Al2O3, and silica contents were slightly more evolved. Things that we kind of knew we were going to find, but came as a little bit of a surprise at the same time. So the SiO2 contents were still around 54, 55% in total composition, which that was something that we've seen through various other explosions and seeing those deposits that were left behind. They range somewhere around 55% too. So we found a lot of plagioclase, olivine, clinopyroxene, titanomagnetite, and apatite, and this was all based on the crystallization state of the expulsions from the volcano. With any good fortune, we will not have a major volcanic event occur in our lifetimes from this volcano, but if it erupts every 20 or 30 years on average, and for the last part of the 20th century, it was about every 10 years, I don't really see this volcano coming to a stop anytime soon. So the gateway to hell is going to remain the gateway to hell.